So let's this my recording is acting funny, so I hope it's okay. So we're talking about challenges of deep learning applications to Earth system science. Let's read some specific points. What are the challenges? We talked already about the way the applications can be very complicated because it's not as simple as what the typical deep learning applications are, with RGB images or no memory and so on and so forth. And Earth system science and geosciences are full of non-local causal links and time memory involved. Interpretability, improving predictive accuracy is important but insufficient. Certainly, interpretability and understanding are crucial, including visualization of the results for analysis by humans. Interpretability has been identified as a potential weakness of deep neural networks, and achieving it is a current focus in deep learning. The field is still far from achieving self-explanatory models and also far from causal discovery from observation data. Yet, we should note that given their complexity, modern Earth system models are in practice often also not easily traceable back to their assumptions, limiting their interpretability too. So sometimes we have a fully non-linear model with all kind of emergent solutions possible, and you get something and then you have to interpret it. Then you resort to things called sensitivity studies, so you turn things off and try to see what happens to a particular result you are getting, and to track back to the originality, or not originality, track back to the origin of the pattern you are seeing, or the evolution of a particular unknown solution, or if something suddenly explodes, what is causing that. Physical consistency is always important. Deep learning models can fit observations very well, but predictions may be physically inconsistent or implausible owing to extrapolation or observational biases, for example. So it doesn't have any dynamics physics in it, so it just takes the data and does a so-called data-driven model, and it may produce hail in the middle of a desert without any circulation to support it, for example, just as a random example. Integration of domain knowledge and achievement of physical consistency by teaching models about the governing physical rules of the Earth system can provide very strong theoretical constraints on top of the observational ones. Thirdly, complex and uncertain data. Deep learning methods are needed to cope with complex statistics, multiple outputs, different noise sources, and high dimensional spaces. New network topologies that not only exploit local neighborhood or even at different scales, but also long-range relationships, as we talked about before in teleconnections, are urgently needed, but the exact cause-effect relations between variables are not clear in advance and need to be discovered. Modeling uncertainties will be certainly an important aspect and will require concepts from Bayesian or probabilistic inference to be integrated, directly addressing such uncertainties. Limited labels. Deep learning methods are needed to learn from few labeled examples while exploiting the wealth of information in related unlabeled observations. These methods include unsupervised density modeling, feature extraction, semi-supervised learning, and domain adaptation. Well, complicated, but we saw this a little bit before. It's very technical. If you don't understand it, don't worry about it. Computational demand is easy to understand. There is a huge technical challenge regarding the high computational cost of current geoscience problems. An excellent example of how to address this is Google's Earth Engine, which allowed the solution of real problems from deforestation to lake monitoring, and is expected to follow up with deep learning applications in the future. So this article is a few years old. I have now podcasts before this on AI for forecasting, medium range forecasting, where I've used the Google Earth's paper on how they do it, and mainly in terms of how much faster and more accurate, more skillful they are compared to dynamic models. Doesn't mean dynamic models are going to go extinct anytime soon, but this approach here of integration with physical modeling is critical. Historically, physical modeling and machine learning have often been treated as two different fields with very different scientific paradigms, theory-driven versus data-driven. So you have first principles, Navier-Stokes equations, thermodynamics, energy balance, and mass balance, and so on, that you are using to do dynamical models, but AI, deep learning, etc. just jump into data and they don't need to know any of the physics behind them. Of course, that's what causes interpretability and other issues. Yet in fact these approaches are complementary, with physical approaches in principle being directly interpretable and offering the potential of extrapolation beyond observed conditions, whereas data-driven approaches are highly flexible in adapting to data and are amenable to finding unexpected patterns or surprises or emergent solutions. The synergy between the two approaches has been gaining attention, expressed in benchmarking initiatives and in concepts such as emergent constraints. This is now a new buzzword that gets used a lot. Here we argue that advances in machine learning and in observational and simulation capabilities within the earth sciences offer an opportunity to integrate simulation and data science approaches more intensively in multiple ways. From a systems modeling point of view, there are 5 points of potential synergies, which we will see in this figure now, in which the numbered circles correspond to the following numbered list. So let me show the numbered list first and then I will come back. So improving parameterizations, we'll come back and look at the figure in detail. Replacing physical submodel with a machine learning model. So radiative transfer model is an example used, and it's a nice example in fact. Analysis of model observation mismatch. Here there's a cost function involved, which is not unusual. We do it for data simulation as well to blend the data smoothly, covariances and so on, and constraining the submodels here as well. So ML, the third module, analysis model observation mismatches here as well. We'll come back to that. And the fifth one in this that we will look at is surrogate modeling or emulation. That needs some understanding, so I will read this in more detail. So what are we going to look at? We talked about figure 3. Figure 3 presents a system modeling view that seeks to integrate machine learning into a system model. As an alternative perspective, system knowledge can be integrated into a machine learning framework. This may include design of the network architecture, physical constraints in the cost function for optimization to look at the mismatch of model and data, or expansion of the training data set for undersampled domains, that is physically based data augmentation. For example, for instance, while usually a so-called cost function like ordinary least squares penalizes model data mismatch, it can be modified to also avoid physically implausible predictions for lake temperature modeling. So if you don't know what this means, don't worry about it. Basically, you define the difference between model and data, and you create something called a cost function, which needs to minimize the difference between the two, and that has ways of doing it, which is used very commonly in data simulation, as I said, with different approaches within data simulation. Here we are talking about deep learning and integrating physical and deep learning models to also go after the mismatch and reducing the cost function in terms of reducing the difference between model simulations and observations. As a byproduct, sorry, did I skip it? The integration of physics and machine learning models may not only achieve improved performance and generalizations, but perhaps more importantly, incorporates the consistency and credibility of the machine learning models. As a byproduct, the hybridization has an interesting regularization effect, given that the physics discards implausible models. Therefore, physics-aware machine learning models should combat overfitting better, especially in low to medium sample sized data sets. So we looked at the time series forecast before about humidity. Humidity overshoots, undershoots, etc. And the statistical approaches, whether it's deep learning, machine learning, or just simple regression statistics, other things, they tend to try to overfit, and can be an issue. So here, physically aware deep learning and machine learning can actually combat overfitting better, especially when you have sample size issues in terms of how much information you are giving for going forward as forecasts, let's say. This notion is also related to the direction of attaining explainable and interpretable machine learning models. So explainable AI is given in this reference in 82, and to combining logic rules with deep learning neural networks. Okay, so I'll come back and maybe read in more detail this particular thing, or maybe we'll keep going because this is only 10 minutes. So let's go ahead and look at this in a bit more detail. So here is figure 3 that we are talking about integrating AI, ML, DL with physical models. Linkages between physical models and machine learning, an abstraction of a part of a physical system. For example, an Earth system model is depicted here. So we're just schematically saying forcing and observations coming in, so that goes input as submodel here, and then from observations you are doing some kind of a parameterization at a meta model level 1, which gives you parameters for the model, which feeds into the submodel. So input coming from here, parameters from here, which gives you an output, and then you have to validate it against ground truthing. So you need to set up a cost function, and ML can help here in analysis of model observation mismatch. Okay, so the model consists of submodels. Each submodel has parameters and forcing variables as inputs and produces output, which can be input or forcing to another submodel. So let's say winds move humidity, humidity goes into the rain or convection model. Data-driven learning approaches can be helpful in various instances, as indicated by the circled numbers. For example, circle number label 2 represents hybrid modeling. So we'll look at the text in a minute on that, or we are already reading that. So here this is about using AI to improving model parameterization itself. So typically all the convections so far have been done with observation-based convective triggers or convective parameterizations, broadly as we call them, and we realize they are deficient. So then we do things like dynamically based convective momentum transports, plume dilution or dilute plume approximation, attempts to improve empirical convective parameterizations, and then we are also gone in the direction of explicit convection or convection resolving models, cloud resolving models, and so on and so forth. But machine learning can allow us to improve the parameters themselves, which then can help the submodel here to replace either a physical submodel with machine learning model, or just improving parameterization that's feeding the submodel, so that you can improve the output, and then also use ML to do analysis of mismatch here. So third is analysis of model observation mismatch, and fourth is of course constraining submodels. As we said, dynamically aware ML can help here. So again, you are getting parameters in submodel 1 again, but now you are feeding it output from some kind of a iterative approach. Let's say AI helped you improve the parameters here, provided the output goes in as input to another submodel where another set of parameters are coming in, and let's say you have to again see if in fact the mismatch got improved because of this approach of improving or replacing the physical submodel with machine learning model, and radiative transfer is the example that's good for looking at this. Okay, so constraining submodels. And fifth one here, I'll come back and look at this figure in a minute. Surrogate modeling or emulation. What do we mean? Emulation of the full or specific parts of a physical model can be useful for computational efficiency or traceability reasons. So you can just take out a submodule and run it separately in offline mode, as they're called. Machine learning emulators, once trained, can achieve simulations orders of magnitude faster than the original physical model without sacrificing much accuracy. Much is a kind of subjective word, right? What do you mean by much accuracy? How important can that be? You know, rain versus no rain is not much. It's not a small change in accuracy, right? This follows for fast sensitivity analysis, model parameter calibration, and derivation of confidence intervals for the estimates. For example, machine learning emulators are used to replace computationally expensive physics-based radiative transfer models of the interactions between radiation, vegetation, and atmosphere, which are critical for interpretation and assimilation of land surface remote sensing into models. Sounds like a lot of things, but basically dynamic consistency is used between radiation, vegetation, and atmosphere, evapotranspiration, and so on, to make sure that machine learning model emulator that is replacing this physical model and testing something is as accurately as possible representing the physical processes that you want to physically model but want to test it offline. Emulators are also used in dynamic modeling where states are evolving, for example in climate modeling, and more recently explored in vegetation dynamic models. We'll look at an example a little bit later. Further, given the complexity of physical models, emulation challenges are very good testbeds in which to explore the potential of machine learning and deep learning approaches to extrapolate outside the range of training conditions. Okay, so that's about integrating physical and machine learning models. It's getting a bit long, but let me go ahead and look at this because this is a supplementary figure that relates to the figure we just looked at, figure 3. So this is one end where you're just purely data driven, and here theoretical or hypothesis driven. You collect data, you analyze data, it points to a hypothesis, you formulate the hypothesis, you gather more data to test the hypothesis. The hypothesis tests positive, formulate a theory, and then you go forward with it, and you keep on collecting data. If any data contradicts the theory, then you have to go back to the drawing board and see what needs to be learned or changed. So this is a cycle of hypothesis generation and testing in complex systems involving process-based models and extraction of patterns from observations. Such patterns are only a surprise and constitute a puzzle if state-of-the-art theory and models do not predict them. So you may have already done something to come from this end, but then some surprise emerges when you do data-driven modeling, and then that has to be understood better. So machine learning allows to extract hidden and complex patterns which should be confronted with model patterns, which means models must emulate reality as seen in data-driven models which are not physics-based, right? So you have observed patterns here. They generate a hypothesis and explain in this case, and you have feedback with predicted patterns from the model's side, hypothesis-driven side. So they can be new and deductive. So you're just deducing from the data, or something emerges out of it. And you want to test the new hypothesis by getting more data or building a model and so on. And hypothesis here from this side combines with existing knowledge to assemble principles of process knowledge or theory, and you implement a model and apply it in an experiment to produce predicted patterns which have to be confronted by observed patterns. Is there any surprise? So model data integration can happen, and then you look for any interesting puzzle that may emerge, which may again lead to generation of new hypothesis, essentially again saying that machine learning allows to extract hidden and complex patterns which should be confronted with modeled patterns. It's a bit wordy and descriptive, but I think you're getting a sense that essentially we have been doing a lot of statistical modeling and statistical predictions for monsoon, for example, which always failed miserably. Then you have dynamic models which are skillful, but sometimes they completely misfire. And then you have data-driven models now generating all sorts of excitement, but they can produce garbage sometimes, problems with interpretability and so on that we looked at before, right? So I won't go all the way back. So let's leave this here and come back and look at what we can do with interpretation of hybrid modeling as deepening a deep learning architecture. So we'll talk actively about integration of physical and machine learning models. Okay.